So we'll talk briefly about other flow similarities that you can, have to pay attention to if you're studying a fluid flow in experimental systems. So let's suppose we're actually going to try to model this wing. It has some chord length L1, it has some thickness at this point T1, and some angle of attack, say alpha. If you're going to model that in a smaller system, then of course your geometric similarity is going to require that your ratio of L2 and T2 remain the same. In addition, all the angles will have to remain the same. So your angle of attack alpha will have to remain the same, of course. This is assuming the flow is coming in like this, some u infinity. And you're going to have all the angles, these little angles here are all going to have to be the same too. So little angles separating lines are going to have to be the same as each other. So all the angles have to be the same. Basically, the way to think of it is if you took a picture of this, and you guys do this with your phones all the time, and you shrunk the picture uniformly in all dimensions at the same, that's what it has to be like. So everything has to be proportional, and all the angles have to be identical to what they were before. So that's your geometric similarity. Your dynamic similarity for this flow, it's going to be the Reynolds number again, because if it's an incompressible flow around this object, and when there's no other fluid in the problem, you're going to have just that one dynamic issue. So you're going to have, be able to simulate this flow if you use a situation where you have the same Reynolds number and geometric similarity. On the other hand, if you get faster, of course, this flow is going to have compressible effects, in which case you'd have to match Mach numbers as well. As you got up closer to the speed of sound, you'd have to have matching Mach numbers in order to get the same effect. If you, for different types of flows, like flows that involve like waves, if you have water and air, you have different things you have to match. So this would not be enough to just match Reynolds numbers. You'd have to match other parameters. If you had that, as I said, if you have any kind of compressibility effects, you have to match the Mach number. If you have some kind of intermittent forcing that's going on, like something's driving the flow with, say, a paddle wheel or something, or a propeller blade that's moving at a certain frequency, then you have to match another set of dimensionless parameters. So there are many, many parameters that can be matched to really simulate a flow accurately. In many cases, it is not really possible to match all the required parameters. So for some flows, they just can't do it. So there are many dimensionless parameters that may need to be matched for flows with periodic forcing, or interfaces with other fluids, etc. In many cases, it's not really possible to match all those parameters, so sometimes it's important to just pick out the most important ones and run your experiments, in such a way that you capture the dynamics that are the most important to you. But that's if you always go on to be experimental fluid dynamicists, then you'll have to study all of these different parameters. But for this class, we're going to focus on that incompressible single fluid flow, in which case you need geometric similarity, and the dynamic similarity is accomplished by matching the Reynolds numbers.